Good morning. Hope all of you have joined the channel. Now let me continue from where I left last time. Just to get back to that non-uniqueness example which we have considered. I just recall it. This was this one, y derivative equal to y to the power 1 by 3. It's a non-linear problem. Okay, and we have if you just look at this, so this gives dy by dx 1 by 3. So this is your f of xy. Now you know that if you look at see, the initial data that we have looked at is this y0 equal to 0. Then we found that there are two solutions for this initial value problem, and thereby give an example where the uniqueness is not valid. And we found that mere continuity of the function, after all, it's a very good function. I mean, you know, there is no problem about the continuity at all. It's a continuous function. But in the neighborhood of the real line, this is the point where we are giving the initial data, and you see that there is a problem there, because you see that this function is not satisfying the Lipschitz condition. In fact, even if you take this one df by dy, this turns out to be 1/3 y to the power minus 2 by 3, and that gives problem in the neighborhood of this point when y equal to 0. This is the line y equal to 0, and you have difficulty there. It becomes unbounded. So that contributes to the non-uniqueness of the problem, and that situation does not arise if you take a point, or if you prescribe your initial data at some location where the partial derivative becomes bounded, or this partial derivative exists and is bounded, or the function satisfies the Lipschitz condition. Because for the function to satisfy the Lipschitz condition, it need not be differentiable. For example, you have seen this function fxy is equal to mod y. This satisfies the Lipschitz condition, but it's not differentiable at y equal to 0. So this is only a sufficient condition that I have been talking about. That's about that. Now you see that we have observed that the solutions are of this form. There is this identically 0 solution, and there is also another solution that we have observed here. Now, why such a sort of bifurcation takes place here? Why there are two solutions for this? Let me try to advance a dynamical explanation to this. Suppose this is the line along which a particle is moving, and x is the time, x variable is the time variable. Now you see you have this 0, and at 0 you are keeping the particle at 0, and then under this particular system, that is, there is a velocity field. You see that dy by dx now becomes f of xy would become a velocity field, and this particle is moving in that velocity field. Okay, so that's a sort of a dynamical scenario that you have. Therefore, if it is positive, you see that it will start moving in this direction. If it is negative, it will start moving backward. That is what happens. Now let us go to the second derivative. What is d2y by dx square? Here x takes a time variable. in the dynamical scenario. So this is equal to two by 3. This is what you get. And dy by dx is y to the power 1 by 3. Therefore, you end up with 1 by 3 y to the power minus 1 by 3. And you know that the dynamical interpretation for the second derivative is the acceleration. Acceleration is equivalent to a force acting on the system. Okay. Therefore, by Newton's law, that is what turns out to be. The rate of change of momentum is proportional to the impressed force. There, when a particle with a constant mass is taken, then you see that this is going to be this will give you the acceleration is sort of equivalent to the force acting on the system. Therefore, what you see is that at y equal to 0, the force acting on the system has a strong singularity. See, it goes to infinity. Okay. Therefore, at time 0, at y equal to 0, you see that one solution would be y identically equal to 0, satisfying all the requirements of this. The other one is because of the strong singularity in the derivative, that is the second derivative of y, that is on the acceleration. Now there is a pull, there is a sort of situation. There is the status of the particle becomes sort of unstable and starts just moving out. Okay, that's what you are having. See, what happens is that when the force acting or the velocity acting at this system is on this system at the point y equal to 0, what will happen to the particle? The particle will stay all the time there because there is no velocity trying to push it out. But however, if the velocity field is something like y to the power 1 by 3, then the corresponding acceleration is y to the power minus 1 by 3, which is a sort of unbounded in the neighborhood of that, in the neighborhood of y equal to 0. Therefore, what happens? This position that you have here is a very unstable position of the particle. Okay, and what happens is it will start rolling out. Once it starts rolling out, it will start roll out. I mean, it is not going to stop because it will immediately, the velocity field will start acting on this. So it's the instability that you have there because of the speciality of this particular velocity field that you have. This velocity field that you have, this is the velocity field that we have, which is forcing the particle to start moving from there. I'll just give an example. You would have seen the coconut shell or on a surface like this. We'll discuss in the later when we work with stability also. Suppose you balance a marble here. It is possible to do it. I mean, there is no difficulty. We stay there. I mean, but the slightest perturbation, because it's in a very unstable state. Okay, even the slightest perturbation will make it to run around along a sort of one of the radial directions. In which direction it gets perturbed, that's the sort of thing. So this kind of scenario is there. The acceleration or the force acting on the system at this related to the velocity field that you have is having a strong singularity at y equal to 0, and that's the reason why you have instability there, and a second solution start emerging from that. A possibility, a slight perturbation will completely unsettle the whole thing, and that is possibly a dynamical explanation that you can give. And your sort of the Lipschitz condition essentially guarantees that such a situation does not arise, so that you can say if the Lipschitz condition is satisfied along with continuity, then the function has a, or then the equation has a unique solution. So I just wanted to make this remark. Okay. Now let me just set the ground for writing down the existence theorem. We have already seen that using the fundamental inequality, it is quite easy to prove the uniqueness provided the solutions exist. We have not said that the solution exists yet. We have only talked about the approximate solutions. Okay, so we have not yet proved that a solution exists for the initial value problem. All that we have said is that if a solution exists, then it is going to be unique, and this is the last theorem that we have proved, and we use the fundamental inequality to prove this. And you recall also in the proof of the fundamental inequality, we have assumed that the function f satisfies a Lipschitz condition with respect to y. Okay, so let me just set the ground for various things. Now you see you have a domain D. We are assuming f is continuous, and x0, y0 is a point in that. Now what we prove now is a local existence theorem. What do we mean by that? What we mean by that is this: in a neighborhood of x0, a unique solution of the initial value problem exists. This is what we want to prove. You remember our problem is this: y dash is equal to f of xy, y derivative is equal to f of xy, y at x0 equal to y0, and the geometry is that we are searching for a function whose graph passes through the point x0, y0, and at every point the tangent vector to the curve coincides with the vector field that is set by f of xy. Okay. As I said, we are going to start the prove the existence locally. I will worry about the global or how large an interval you can take on which the solution exists. All these questions take up at the next stage. Before that, we take up a sort of, D is open connected. Okay. So what we have is that you take the point x0, y0, it is in D. Now, since this is open, you can find a rectangle with center at the point x0, y0, okay, given by something like this: mod S, the set of all xy, for which mod x minus x0 less than or equal to a, y minus y0 less than or equal to b. That means a rectangle with length 2a units and width 2b units. So this is the position that you have, the rectangle that you have. So this is a units and this is a units and this is b units. So you can now actually find out the coordinates of the vertices and all sorts of things. It is a rectangle that is symmetric about the point x0, y0 in either direction. Okay. Now what we do is I am just setting up the notation. Now you see that this is a closed rectangle. S is closed. It's a closed, bounded, it is also bounded, and since f is continuous, f continuous implies f is bounded. Let M be the bound for this. Mod f xy is less than or equal to m finite on S. This is the M that we have. Take some bound for this. Now what we do is we construct another rectangle. The other rectangle that we consider is this R. R is defined as xy such that mod x minus x0 less than or equal to h. Okay, let me define h. H I define as minimum of a and b by m. Less than or equal to h mod y minus y0 less than or equal to h. Now you can easily see that either, say, if b is equal to mh, okay, what is h? H is the minimum of a and b by m. So you can have a situation where h is equal to a if b by m is greater than a, h is equal to b by m if a is greater than b by m, or if a is equal to b by m, then it is going to be h is equal to a. So these are the three scenarios that can emerge. Okay, let us look at what is the shape of the rectangle that you get. See, all the three scenarios we will consider. So I will just remove some part of it, and then I want to keep that side. I can take out this. Okay, let us take the three situations where, see, one of them is, of course, a is equal to b by m. Then h is equal to a. And in that case, you see that the rectangle that you have would be See, in that case you see that M into A equal to B. Okay, and this is equal to H. Okay, therefore MH equal to B, because H is equal to, this is the situation. In that case what happens? Your R becomes, now we define R. R is defined here. R is the same as S. Okay, now there are two other scenarios that can come. H is equal to A, but A is less than B by M. Okay, therefore what you have is that MH is less than B. MH is less than B. Therefore what happens? See, this is your S. This is A, this is B. Now H is this, and MH is less than B, therefore it is somewhere here. Therefore what you get is this, say a rectangle of this sort. This is your R, and this is your MH, which is equal to MA. Okay, so this is the point X naught, Y naught. So this is your R. Now what happens is, the third scenario is this. H is equal to B by M, and B by M, A is greater than B by M. That is the situation. Therefore what you have? What you have is that A is greater than H. In that case what happens? The rectangle R becomes the following. This is your S, this X naught, Y naught, and H is equal to B by M. A is greater than H, therefore H is somewhere here. H is still positive, and what you have is that this is the rectangle R. This is the rectangle R. And on R, anyway R is, therefore the bound for F is M itself. Okay, so that's the scenario that you know. There are three situations that can come. One is R equal to S, the other one is, in both the cases R is contained in S, but in taking two different situations, one A is equal to H, one is H is equal to B by M. Anyway, what is significant is that given an interior point of D, you can find a rectangle R with the following description. What is the description? The description is that mod X minus X naught less than or equal to H, mod Y minus Y naught, I said this is MH. Okay. Sorry, I think I made a mistake. So this is mod Y minus Y naught less than or equal to MH. Such a rectangle you can find, and that rectangle we designate by R, and on that F is bounded by M. In fact, F is uniformly bounded by M. Okay, so that gives a uniform bound for F. And now this much is clear. So what we are interested at the first stage is to establish an interval X naught minus H to X naught plus H on which the solution of the initial value problem exists. Okay. So let us start now. So let me now state the theorem. So I have got all the technical information required to state the theorem. Okay. Consider the IVP f of xy with the y derivative at x naught equal to y naught, where x naught y naught belongs to D, where f is from D to R a continuous and satisfies ellipsis condition. On B. In fact, it is enough that it satisfies the ellipsis condition on R. Okay. So let us take let R be defined by where M and H are as described above. That is, you start with an S on which M is there, is the bound, and H is given by minimum of A and B by M. Okay. Then there exists an exact solution y let me just put this open. X dot H of the initial value problem on, so this is the theorem. The theorem is the following. That means the initial value problem is given. Now H has been, we started with an S lying inside D, which is possible, centered around the point x naught y naught. Then you can find R, determine R, which involves the bound for F on S, and F is certainly a continuous function on the compact set S, therefore it is bounded, and we use that bound to construct H. And what the theorem says is this: on the interval x naught minus H to x naught plus H, that is the H neighborhood of the point x naught, a solution of the initial value problem, a solution of the initial value problem exists. This is the problem. Right now we are assuming the function to satisfy a Lipschitz condition also. Therefore, lot of results that we have already obtained can be made use of. Hello, yeah, please.
Hello?
Please, yeah, please.
Am I audible?
Can you can ask the question. What is it?
Oh, am I audible?
Yeah, I am audible. You are audible.
So you said that the function is Lipschitz condition with respect to y here on the y side.
Yeah.
But if you say that the function is Lipschitz under a variable y, but how it concludes that it will be continuous in two variables?
You mean the solution? No. If it is Lipschitz, you are saying? No, I am assuming f is continuous on both the variables x and y.
Oh,
Apart from that, on y there is a restriction that it is Lipschitz. Because you know that that puts an extra restriction on the mode of continuity about the variable y.
That is I'm saying that if you say function is Lipschitz condition with respect to one table, we cannot conclude that the function is continuous in two variables.
No, see, Lipschitz assumes continuity or assures continuity with respect to y in the vertical direction. But the function is assumed to be continuous in both x and y. Okay? Is that all right? Yeah, you can intervene whenever you want, because I can use this facility to answer your question. Okay? Thank you. Right. Okay. So how do we prove this? We start using the result that we have constructed earlier, namely the approximate solution. So choose, what we do is we choose a monotonically decreasing sequence epsilon n such that epsilon n goes to 0 as n tends to infinity. Something like 1 by n, which goes to 0 as n tends to infinity. Now you know that you have approximate solutions as we have described earlier on any interval x0 to h, and also from x0 minus h to x0 plus h, you can construct a sort of broken line solution, a broken line function which satisfies the equation approximately. So that is the Cauchy-Euler approximation. Okay. So there exists a sequence yn such that what are the things that you have? These yns are continuous, all the yns are continuous, but each yn fails to be differentiable on a finite set of points, and also you have yn x0, we take the initial data, the same for all this, yn x0 equal to y0, and having the property that yn derivative of x minus f of x is less than or equal to epsilon. That is, the error with which yn satisfies the equation is with the error epsilon for mod x minus x naught. This is the content of the theorem that we did in the beginning. Okay. Now let me now what we want to assert is that this sequence of functions yn uniformly converges to a differentiable function on the interval AB. Okay. Secondly, that becomes a solution of the initial value problem that we have started with. Okay. So we have to give the arguments for that. So let us start working out this. Now what we can say that these yns are not yns are continuous, but yns have problem of differentiability on a finite set of points. Each yn has a set of points on which it will fail to be differentiable. Now this is a problem. That is why you call it an approximate solution of the equation. Now we start building up our argument. So the first part. So step 1. The first step, we assert that yns converge uniformly to a function yx. So this is what we want to prove. A sequence yn this is the first thing that we prove. In fact, on this interval it converges. I mean, that's no problem at all. Okay, let us prove this. What we prove is the following. So we show this by proving that the sequence yn is uniformly quotient. So how do we prove that? So we take let then what we can estimate is this. This is less than or equal to, we are using, see, both yn and ynp are solutions which satisfy the same initial condition. So what we do is we use the fundamental inequality. In the fundamental inequality, we take P to be yn minus yn plus P. And you see that Px0 is 0 because of the both satisfy the same initial condition. Therefore, only the other term gives, survives. So you have this is what you get. Okay. So this comes from this is the second term that is involved in the fundamental inequality. And this is, since we have assumed the sequence to be monotonically decreasing, this is less than or equal to twice epsilon n by k. And in fact, you have mod x minus x naught less than or equal to h. Therefore, this is the bound for this. Now you see that this implies that yn is a Cauchy sequence. So you can immediately run the argument, choose an epsilon, and corresponding to that you have this epsilon and etc. etc. So you have this is a Cauchy sequence converging, okay, which is uniformly Cauchy. On because the estimate that you have here does not depend on the point on the interval mod x minus x naught less than or equal to h. Therefore, it is uniformly Cauchy. So what is that you get? These are all continuous functions. Therefore, this implies yn converges uniformly to a yx continuous. So what we have proved is that ynx is a sequence of continuous functions which converges uniformly on the interval mod x minus x naught less than or equal to h, and therefore it converges to a continuous function. It follows from the completeness of the space C x naught minus h to x naught plus h. Take this space, so space of all continuous functions with what is called a uniform norm, the norm of f being defined, or norm of y is defined as the supremum of mod yx on the interval x naught minus h to x naught plus h with respect to this uniform what is called this particular norm C with this particular norm. Now you see that this is a complete metric space, and therefore every Cauchy sequence converges to a function on that. And because of this uniform convergence, you see that the limiting function is also a continuous function. Now this is what we observe. Now we go to the next step. So in the first step we have proved this. Now we take the step 2. Now you see our strategy is the following. We will see the expression of this technique later. I will just take out the theorem also. Now you all know what the theorem is. Our strategy is something like this. We work a sort of integral equation, convert the initial value problem into an integral equation. What you do is this. See, you have this equation. Yx naught so what we do is, suppose y is a continuous function, a continuous differentiable function, it satisfies this. Okay, then what you can do is you can substitute that function yx, and then you get this one, integral x naught to x y derivative of, I am using a dummy variable, and then this one turns out to be y x minus yx naught. Yx naught is y naught we shall discuss this more detail later, but now you see that, so this initial value problem is completely recast into an integral equation. Okay, conversely, suppose you know a solution of this integral equation, then what happens? The one thing that you observe is that yx naught is equal to y naught, because if you put x equal to x naught here, this term vanishes. Okay. Secondly, this is differentiable. This function has to be differentiable if it satisfies this, and you see that y derivative equal to simply f x yx, or it satisfies the differential equation and also the initial value problem. Therefore, something like we reduce the problem to this integral equation, then you are done. Okay. So let us see what are the problems that you encounter while doing this. So now we look at this one. This is sensible. Consider the sequence what you have is this f t y n t this for each of the functions that we have constructed, approximate functions that we have constructed, that is yns, you consider the sequence of functions. Okay. Now we prove that this approaches uniformly to integral x naught to x f Because y you already have obtained. Y is the limit of the sequence yn. What is the problem here? The problem here is this. What you are writing is the following. Limit n tending to infinity integral x0 x f t yn t dt is equal to integral x0 to x limit n tending to infinity dt, and this we want to write this as you take the limit inside f of t limit this is what you want. So in fact it's a what you want to assert is that you can jump the integral. The limiting operation can jump the integral and jump into the function, so that this is what you get, and this will become simply integral, because the limit of this you know is yt, and therefore you get the result. So this is what we want. So we have to justify the interchange of the limiting operation and the integration, and that's where we use this. Okay, so let us do that. Now we come back to our R. So we need some arguments here. So I think I'll wipe out some part of it. Okay. Now we consider R. You recall what R is? That is mod x minus x naught less than or equal to h, and y minus y naught is less than or equal to mh. And this is of course contained in D, and this is compact, all these information that you have, and we have f is continuous on R. Therefore we want to assert that it is uniformly continuous on R. Okay, right? So what we want to say is that since f is continuous, hence given epsilon positive, there exists delta positive such that mod f of x y1 minus f of x y2 is less than or equal to epsilon for x y1 comma x in that rectangle. Okay, and such that mod y1 minus y2 is less than or equal to delta. So this is something that you can immediately conclude from here. Therefore, now you see we have this epsilon positive we have chosen, and that has given rise to delta positive. Now for this delta positive we do the following. For delta positive, this delta positive, there exists an n such that mod ynx minus yx is less than or equal to delta n greater than n and mod x minus x naught So you can get this as closely as you want on the whole interval mod x minus x naught less. So it is uniformly yn converges to y. That's what we have seen. And this is a consequence of part 1 of your step 1. That's a consequence from step 1. Hence, what we have is this. If n is greater than n, mod f of x minus yes. What you have is this, you know that once you choose, okay, what you have is that you have ynx minus yx is less than or equal to delta. Therefore, use this one. You use this one, what happens is that f of x ynx minus f of x yx, which is something like y1 and y2 replacing there, which is less than delta, and therefore for n greater than n, this is less than or equal to epsilon. So you are using this, okay, which implies f converges uniformly to this we are going to use inside here in this justifying this change of integration. Hence, by the interchange of now you see this justifies our interchange of the limiting operation and the integral operation. We obtain limit n tending to infinity integral x naught to x f t dt. This is equal to integral x naught to x f t y t dt. Okay, that means all this limiting process, this limit can jump inside and then go inside, and then you get this result. So this is the one that we are going to use next. Okay, now we come to step 3. In step 3, we make use of the fact that all these yns are approximate solution of the differential equation in the sense in which we have defined it earlier. Okay? Therefore, let us start there. So, what we want to prove is this. So, we prove that y is differentiable and y derivative and also y x naught equal to 1. This is what we want to prove. So that's what we want to prove. Okay. So let me do that. Now this is not the Picard's approximation theorem. Picard's approximation theorem constructs the approximations in a different way. We'll be looking at that, and what mathematics it generates we will also look at. But before that we will look at this. Okay, let us complete the proof now. Okay, so we have this inequality. We start from this inequality. At the finitely many points where yn derivative is not defined because of this kind of approximation. So you see there are points here where this derivative is not defined. Now we integrate on both sides. That does not really gives any problem on integration. So what you have is this. So what you take this integral x naught to x I am introducing a dummy variable t, which is the usual thing, not to confuse with the x that we are using. dt. Now this I can take this modulus inside and then use this, and from that you get immediately this is less than or equal to epsilon n into mod x minus x naught which is less than or equal to epsilon n. We need one intermediate step where this absolute value is is taken inside. That's very simple. Now what we do is we work with this. So what you get? Therefore you get yn y naught, because you know that every yn satisfies the initial data. Yn at x naught is equal to y naught minus integral f t dt and this is this one and you know that this is less than or equal to epsilon n h from the previous step. Okay, that means, what does this mean? This means this is true for every choice of epsilon n. Epsilon n has been chosen such that n goes to 0, and therefore now going to the limit, it follows that yx this is equal to 0, where y is the limit of the uniform limit of the sequence yn. What does this mean? See, f is continuous and y is also a continuous function, and therefore you see that this is a continuous function and which is differentiable with a derivative which is continuous, therefore y is differentiable. This implies y is differentiable and satisfies So we have shown that there exists a solution to the differential equation or the initial value problem. And the initial value problem, and this also gives you a way of constructing these approximations to the solution, because you see that often the problem that you encounter in differential equations is this: how to solve the equation. So what we need to do is this. What we have proved is this: there exists a solution of the differential equation. That proves the existence theorem. Okay? And we have also seen that under these conditions, if a solution exists, then it is also unique. That we have proved in the last theorem. So combining these two results, what you can assert is that if you look at this initial value problem, where f is assumed to be continuous and on D, and f is satisfying a Lipschitz condition on D, for x0, y0 belonging to D, there exists a H positive, so that on an interval mod x minus x0 less than or equal to H, there exists a unique solution of the initial value problem. So we have proved the existence and uniqueness theorem, and in that we have assumed f is Lipschitz, and that is a crucial condition other than continuity that we have assumed. And later on I will show you that the Lipschitz, if you knock down or knock out the Lipschitz condition and just keep the continuity, you may not be able to get the uniqueness. As we have seen with an example, it is amply clear that you cannot you need not expect. Under some circumstances, you are going to be in trouble and you may not get uniqueness at all. But still, there exists solution. In fact, the problem is plenty. That is, there are more than one solution which satisfies the same initial data. So we prove that under the assumption f is continuous and not assuming Lipschitz condition, you may have difficulty in getting the uniqueness of the solution and existence of this. In this context, what a nice, the concept of equicontinuity comes, and also what is called the problems of, what you can say is that in the sequence you can, here you are able to say that there is a unique limit for this sequence. That uniqueness may not exist. There may be several subsequences which converge, and each subsequence may converge to a particular limit, and each one would become a solution of the equation. I will explain this out in my next part of the lecture. So we have proved the major result, namely the existence and uniqueness. In fact, if you look at it, what it says is the following. Given a initial value problem with proper conditions on f, like the Lipschitz condition, there exists a unique solution of the initial value problem. Yeah, there is a unique solution of the initial value problem on some interval. So locally, in the neighborhood of the point x0, you see this is the point x0, there is a neighborhood of that in which you can assert that there exists a unique solution for the initial value problem. So it's a local existence theorem. There are questions like on how large an interval you can define the solution, or a solution exists. For example, if you take this problem, a very simple problem, y derivative equal to y. You can solve it actually when there is no problem at all with say y 0 equal to 1 or something like that. Then you see that the solution is yx equal to e to the power x, or more generally put some x0 here, then you see that this is going to be x0, oh sorry, y0, then this is going to be y0 times e to the power x. Now you see that this is defined for minus infinity to plus infinity on the entire interval. Okay. In fact, later you will see, or one can prove that for a linear equation, the solution is defined on the entire interval. Okay. So that's not difficult to prove. But before that, let us look at, so when the problem is nonlinear, that means the function f of xy is not linear in y, then you cannot probably expect this. I will give a very interesting example. The example is this. Consider this equation. So your f of xy does not depend on x explicitly, but depends only on y, and its dependence is given by y square. And we also, so the problem is defined. Now you see that f is, or the d you have in this case is R. So the whole of R2 is defined. Now the question that you ask is this: suppose some point in R, is it possible to solve or what is the solution? What is the solution? Satisfying the initial data yx not equal to y. Okay, what do you have? Let us analyze it without really solving it. Let us get some insight into the nature of the solution. So this is R2, which is taken as D, where f is defined, f is continuous. Is f Lipschitz? Let us investigate this, because you see that df by dy equal to 2y, and you see that on any region of the form mod y is less than or equal to k, to k, and is that means mod y less than or equal to k is on a strip like this. But you see that the bound gets larger and larger if you go farther away from the line y equal to 0. This is x axis, this is y axis. So the function is Lipschitz with the Lipschitz constant 2k. That's what you see. So you see that f of in this particular region, you call this R also, in this case. So we want to solve this equation. So let us analyze it further. Now suppose, let us take the trivial scenario. That means you are at some point, that is the initial condition. Then you see that the velocity field that you have, you go to the dynamical interpretation, is 0. What does it mean? For all x, it is going to be the graph of the solution will be y identically equal to 0. Okay. So the only solution that the equation has is y identically equal to 0, which is defined on the entire interval minus infinity to plus infinity. Now we take this situation, y naught is positive. So you have a point here, x naught. This is x naught, y naught. This is the initial point. Now you have the existence of the solution and so on. So before we solve this equation explicitly, which is not difficult, you observe that f is positive here and f is negative here. What does that give? That gives some information about y. Because what is our equation? Our equation is that df by or dy by dx equal to f. And you see that if you are in the upper half plane, then this is therefore what you can infer is that, okay, so what you have is that dy by dx is positive so also these are the situations that you have. What does it indicate? It indicates that y is, so here it says that y is monotonically increasing. Here y is monotonically decreasing. Oh, sorry. I'm sorry. Here also it is positive, but this is therefore this is monotonically decreasing. Sorry, because we are taking f of xy is equal to y square, and y square is always positive. So in both these situations, y is a monotonically increasing function. And you also observe that the graph grows sharper as y tends to infinity, plus infinity or minus infinity, because y square increases sharper. Okay, so dy by dx is also not only positive, but it is monotonically increasing with y. Okay. So as y gets sharper, it increases. It increases rapidly. So the question that you have is this: is okay. So let us start investigating this. So you can solve this equation and you can show that if the initial data is or x naught y naught as a point in this, and I am assuming x y naught not equal to 0, then you can show that yx is equal to the initial value problem, and that's quite easy to. So you integrate this, integrate it, and apply the initial condition that yx naught is equal to y naught, and then simplify. You will see that this is the solution of the equation. I don't want to spend time on that. I leave it you to compute the solution. Let us investigate what happens with this function. Let us take the case 2, where y naught is positive. That means you have taken a point. See, x naught can be anywhere. I mean, it is immaterial. This is the point x naught. This is the initial point. What can you say about y? See, we are assuming y naught is positive, and for 1 minus, when x minus x naught, see 1 minus is positive. What is that condition? That is y naught into x minus x naught less than 1 upon y naught. X minus x naught less than or equal to, so or x is less than x naught plus 1 by y naught. Y naught is positive, so you see, you take the point x naught plus 1 by y naught. Y naught is positive, therefore it is some point on this side. Okay, and to the right of this. So you see that the function y tends to as x tends to 1 by and x is of course less than So on this side, you see that the function, the solution is a monotonically increasing function, and which has the see, the graph stays in the upper half plane, because this number is that x, y, x is always positive on this part of the interval. And what happens is, this becomes an asymptotic line, and you see that the graph of the function takes the form something like this. Sorry, not this one. This one will be the asymptotic line, and this is the point which passes through that, and then it sharply increases and goes like this. So this is the solution yx. So, and x naught lies on this interval provided you are to the x naught plus 1 by y naught is to the right. So only over here the initial data will be satisfied, not here. So the particular solution is defined only on the interval minus infinity to x naught plus 1 by y naught. You see that the limit, the interval on which the solution is defined is confined to an interval, and it is for each solution or for each initial data there is a corresponding interval on which the solution is defined. So it is not like the linear problem. Here the solution will be defined, each solution will have an interval on which it is defined. Okay. So you cannot make a universal statement that the solution is defined everywhere from minus infinity to plus infinity, even if the function is a very dignified function. So fxy equal to y square is a very smooth function. It's a very smooth function. Satisfies the Lipschitz condition also. So there is no difficulty at all about that function. Nothing wrong about that function. Nevertheless, you see that each solution has its own interval on which it is defined. So you cannot make a universal statement that just by looking at the function f of xy is smooth enough. One cannot immediately come to a conclusion that the solution is defined on the entire interval. Therefore, the question where the solution is defined, where the solution of the initial value problem is defined is relevant. Okay. So if your point is somewhere here, if your x naught is somewhere here, then you see that it's going to be defined somewhere here up to a certain case, but not beyond that. Okay. And you see that the graph always lies in the upper half plane. It is defined from minus infinity to this particular point. You can make a similar analysis, or I leave it to you. Analyze the case where y naught is negative. There also the solution is positive. And what is the behavior of the solution? The behavior of this solution is that as y goes to minus infinity, it goes to 0. Okay? And it asymptotically grows to plus infinity as x moves towards x naught plus 1 by y naught. Similarly, you can make an analysis for the case y naught is less than 0, which means you are taking the initial data as a point in the lower half plane. In that case, where the solution is defined, that you analyze. This is similar analysis would work. Okay. So I leave that to you. So the question, even for very smooth functions, the interval on which the solution is defined is really something which cannot be, no universal statement can be made as it is. But there are situations where, in the case of problems or linear problems, generally you can make some statement about it. So we will take up this interval on which the solution is defined as the next step. Right now what we have said is that there is some neighborhood, however small it may be, the solution is defined. I want to make one more remark. Going back to the example that we have considered for non-uniqueness. Let me make another remark on this. So you take this problem. First of all, I want to, we started with y0 equal to 0, but even if yx not equal to 0, see the way in which the solution looks like is this is the point as the initial data. Then you see that the identically 0 function is a solution, and then a solution of this type always exists. There are two solutions that you can define. The solution is given by two by 3 x minus x naught This is the second solution. Y identically 0 is one solution, second solution is this. Now you see that the problem that you encounter is this. First of all, your f of xy does not depend on x, okay, and has problem at y equal to 0, which is not on continuity, but it does not satisfy Lipschitz condition, and the neighborhood of this particular line y equal to 0. This is the line y equal to 0. Okay, that we have proved already. Suppose your initial data is where y naught is positive, not equal to 0. Then no matter how close the point x naught y naught is, you can find a neighborhood which is lying in the upper half plane, which does not have any part of the line y equal to 0 in it. Okay, right? As long as this condition is satisfied, there exists a neighborhood of the point x naught y naught which lies in the upper half plane, and no part of the line y equal to 0 is in it. Therefore, what you can do, you can construct a rectangle S inside that, and then a corresponding R, then a corresponding H positive, so that there is some interval on which mod x minus x naught less than or equal to H, there will be a unique solution defined. But that is defined only on that interval, and how far you can go will depend on the solution, or how far away you stay from this line. So this is the line where you are having trouble, that is y equal to 0 is the line along which this function fails to satisfy the Lipschitz condition. Whereas if you stay away from here, you see that it satisfies the Lipschitz condition. Because if you take the partial derivative of that, see that it is 1 by 3 y to the power minus 2 by 3, and that is bounded as far as this part is concerned. If you stay away from here, only in the neighborhood of y equal to 0, you get into trouble. Otherwise, everything is fine. It is bounded. Therefore, the Lipschitz condition is satisfied in that case. Okay, right? And therefore, our existence and uniqueness theorem applies there. Okay. So this is the line. No matter where you prescribe your initial data on this line, you won't get uniqueness. Okay. That is the problem. So I think I just wanted to make those remarks about the solutions. Now, what I want to say is this. See, if you look at the solution that we have obtained and the way in which we have proved it also, or just apply the fundamental inequality. What does the fundamental inequality say? You have two approximate functions, y1 and y2, e to the power, I'll just write down the inequality, this is what you get. This is the fundamental inequality. So you have where epsilon is, see, y1 satisfies with error epsilon 1, y2 satisfies the equation approximately with error epsilon 2, then epsilon is equal to epsilon 1 plus epsilon 2, and k is the Lipschitz constant, etc. I say this is a beautiful inequality to estimate the error. Okay. Suppose you take this equation, y derivative is equal to f of xy, and suppose you know that the solution exists on mod x minus x naught less than or equal to h. We assume f is Lipschitz with constant k on R, where R is as we have defined on this. Now suppose you take, see, our physical, the difficulty is that what we have proved is given x naught y naught, there exists a unique solution in some interval surrounding the point x naught, and whose graph may be something like this, which we don't know. Unfortunately, we don't know exactly this solution except in some handful of examples. But in general, we do not know. We are not able to exactly write down the solution through this. What we are told is that there exists a function with such and such properties and satisfying the initial data, which is defined on the interval x naught to x naught minus h to x naught plus h. where it is an exact solution of the differential equation. This is what we have proved. Although what we can do is just construct an approximation to this particular solution. That is using the Cauchy-Euler method. You can start from this point, draw a line, so it goes like this. Just recall what it is. So this is a way of getting an approximate solution, a solution which lies closely to the actual solution. And how close also we can determine. See, the solution is this. Let me just write this. Okay. How I do this is as follows. You see, I start from the point x0, y0. I know what f x0, y0 is. I draw a line segment and then go up to an interval x1 with that slope. Then I compute f of x1, y1. Now this is the point x1, y1. I compute f of x1, y1. I draw a line and then come to the point x2 and so on. So this is how I construct the Cauchy-Euler approximation. I can always do that. There is no difficulty. Okay. Now what I have proved is that it actually converges on some interval x0 to x0 minus h to x0 plus h. And then suppose you have the exact solution yx and an approximate solution y tilde of x. And y tilde of x has the yx has the property that y derivative of x is equal to f of x yx mod x minus x naught less than or equal to h. And of course yx naught is equal to y naught. Then you have a solution y tilde of x with the property that y tilde x minus f x y tilde x where y tilde derivative does not exist on a finite set of points. The left derivative and right derivative exists at those points. There is no difficulty. So there is a jump discontinuity that you can have for the derivative. So the simple discontinuity that you have for the derivative. So derivative is a function with simple discontinuity at finite set of points. Now apply this result. What do you have? Take this one, y minus y tilde. Estimate this. This is less than or equal to. Now you see both y and y tilde are assumed to satisfy the same condition. Therefore what do you get? It's 0. Okay? Because they satisfy the same initial data. And the other part is the error. Error is, you see, exact solution satisfies the equation with error 0. So your epsilon 1 is 0 and epsilon 2 is given by epsilon. So you have epsilon divided by k is the Lipschitz constant into e to the power k into x minus x naught minus 1. This is the estimate that you get. Therefore, what do you get? What is that? What is the yx minus y tilde x You can get an upper estimate on the whole interval. You see that this is going to be epsilon by k and e to the power k h minus 1. This is an error estimate that you have. You do not know what the solution is, but you can compute this. Okay? You can compute this. You do not know what the solution is. You may not be able to do it. Exactly write down the solution. But what you can say is that the solution I have constructed satisfies the equation approximately with the error at each point bounded by this particular number. Okay? So if h is small, you see that the error is going to be very small. It depends on also epsilon. So how you have constructed y tilde. Okay, so you can keep this small. If you keep this small, so in the neighborhood of the point x naught, in the very close neighborhood of that, the error is going to be small. It may get blown up depending on what h is, but this gives an estimate of the error that you have. Okay, so this is the case. Okay, so we will write down that result. An exact solution existence and uniqueness theorem. On let y tilde be an approximate solution of the initial value problem, same initial value problem with error epsilon. Up to an error epsilon. That means this condition is satisfied. Such that was yx naught equal to y tilde x naught equal to y naught. Y naught, same thing. Then there exists an n positive such that mod yx on mod x minus x naught Now this one follows from this inequality. See, all that you need to do is write we have the inequality yx minus and write this actually estimates the error in the choice of an approximate solution. How it is related to this, and it is linked up with the Lipschitz constant, etc. It's clear. Now what you can do is the following. Take some example. Y derivative equal to y on the interval minus 1 to 1 with the interval length, okay, with the partition sorry, just a simple computation that you have. and then compare with the function which is the solution of the you know the exact solution, you know the approximate solution, and then work it out, but exactly compute this solution. Okay, starting from this is the breakup. Sorry, this is the breakup. So it's equal to 1 by 4. Sorry. Therefore, there are 8 subintervals of this. Okay, so this is minus half. This is half 3 by 4 minus 1 by 4 minus 3 by 4 3 by 4 1. Starting from here, you compute the solution. Okay. Now compare it with e to the power x. That is the exact solution of that. Okay. Right. Okay, now what I want to do is the following. I'm going to do it today. I said the Lipschitz condition is important in getting the uniqueness. That means only with some extra condition on the function with respect to y you will get uniqueness. Otherwise you may not get uniqueness at all. That we have already seen. Now what we want to do is this. Can you at least say that the solution exists provided even in the absence of a Lipschitz condition? That means I will be assuming that the function is continuous. But I am not going to assume that it is going to be Lipschitz with respect to y. Is it possible for me to assert that the solution exists on some interval? There may be one solution or many solutions, but at least you are assured that there is one solution which exists on some interval x0 minus h to x0 plus h. Is it possible for me to prove it? Okay. We will investigate this problem next, and you will see that some beautiful ideas in analysis do come from here. So I will take it up next class and we will discuss it next time. Okay. So thank you very much. Do you have any questions? Do you have any questions? Om Prakash and Riddhiman?
No, sir.
Okay, fine. Right. Thank you very much.